Hello everyone, and welcome to this talk about the Julia programming language. So my name is Eric Engheim, and this is a talk that I had at the ACCU conference. Now, unfortunately, the recording I have from this talk at the conference isn't that great, but I've noticed that there's a number of people that really like this talk, so I thought I should do another recording of it that hopefully is of a bit better quality. Just to introduce myself a little bit, I'm based in Oslo, Norway. I work for a company called 60 North. We do Python training and Julia training. So one of the things I do is I teach beginners the Julia programming language. So this is a kind of introduction to Julia, not really teaching you the language, but I'm trying to give a little bit of a sense of what's the big deal of Julia, what's the advantages, and what is it that Julia brings to the table. So let's get started. So how did Julia come about? Well, I try to popularize this a little bit with this little example. Basically, there was a discussion going on, or has been going on for many years in the scientific community, where they've been using a lot of languages like Fortran, and people don't like using Fortran. So what has been the solution? Well, for a long time now, people have been using other languages like Python or MATLAB or R or maybe even Ruby. They're more fun or exciting to work with, or at least a lot more productive. You can get code written much faster. But there's a catch. These languages are slow. And so the mantra has been, if you want to have high performance language, it's got to be statically typed. It has to be something like Fortran or C or C++. So what people have been doing is that they've been combining both approaches. The really performance-sensitive parts have been rewritten as C or C++ or even Fortran modules, and then a slower language like Python or R would call into these. But this is not an ideal situation. It creates what we call the two-language problem, which means you constantly have to juggle these two different languages. You might find that you created some new code for which there is no high performance module, so you have to write one in C++, or maybe it isn't something that you can easily utilize an existing module for. So ideally, we would want a dynamic language, but the consensus has been that's just not possible. I meet this attitude all the time. It's very hard to get across that Julia is in fact a very fast language, because people are so caught up in this idea that dynamic equals slow. It's just not taken serious. But these guys, the creators of Julia, proved everybody wrong. So here we got, starting from left, Stephen Karpinski, Viral Shah, Jeff Bezanson, and Professor Alan Edelman. So what exactly was it that they did? Well, they figured out something by studying all these different code bases for dynamic languages. And that the idea is, if you can act like a statically typed language whenever possible, you might actually get comparable speed. And it turns out that dynamically typed languages are written in such a fashion that 90% of the time, they could have been a statically typed language. What I mean by that is that the dynamic features of these languages are really only used 10% of the time. So, what exactly is Julia? Well, it's a general purpose, dynamically typed, high performance, just-in-time compiled, multi-platform numerical language. Well, that's a mouthful. And some of this sounds like a little bit of a contradiction in terms. How can it be a general purpose and a numerical language? Well, by that I mean it's not like a NextR or MATLAB, which are kind of special purpose languages. This is intended to be something more akin to Python or Ruby or maybe even JavaScript. It's supposed to be possible to use Julia to write any kind of programs, whether that's a script or maybe a web server or something similar. However, unlike Python, Ruby, etc., Julia has been created also as a first-class numerical language, but that would mean that numbers are first-class objects in Julia. You could even add your own specific number types, and you're going to get the same kind of performance as you would get with the built-in types. And by dynamically typed, I hope you're already familiar with this term, we mean the languages like Ruby, JavaScript, Lua, and so on, as opposed to C and C++, Fortran, Java, C#, and so on. These are languages, or dynamic languages, are such where the type information is stored with the objects at runtime. So when the programs are running, you can inspect or ask the objects what their type is. So this is utilized at runtime to avoid using incompatible types with each other. However, you cannot catch at compilation time whether objects are used wrong. That's something you could do with statically typed language. You can't catch all the cases, but you can catch a lot more of them. So what about just-in-time compilation? You might have heard about that in languages like JavaScript or Java. Now, these are very different forms of just-in-time compilers. These are what we call tracing JIT compilers. And Julia is a very different kind of, or Julia uses a very different kind of just-in-time compiler called a method compiler. This is a much simpler kind of just-in-time compiler. And later we will get more into why that is significant. So when I talk about Julia to people, I often get this question, well, where is it used? What are some big important application that I've used that has been implemented in Julia? That's not a question that's easy to answer, because Julia isn't really the thing that you use to make, I don't know, cell phone applications or web pages, at least not yet. Instead, you will find Julia in larger projects like the Celeste project. Now, this is trying to catalog all the photos that we've taken of the night sky, and that's a lot of data. At the moment, these have to be manually searched, and that's a big job. To categorize or catalog all this data, they are running Julia software on a supercomputer with 650,000 cores, processing 178 terabytes of data. So Julia is actually among the very few, actually the only dynamically typed language which is being run today on supercomputers. And if you're curious about this, this is actually a project that you can find online. It's an open source project. Let's do another example. The next generation climate models, that's a big thing for our future, is going to be built using Julia. And these aren't just anybody doing this. This is scientists from Caltech, from Massachusetts Institute of Technology, from NASA Jet Propulsion Laboratory. So these guys had this kind of bake-off test where they pitted different programming languages against each other to figure out, how are they going to build this next generation climate model. And what they found to their surprise was a kind of high-level, high-productivity language like Julia was only a few percentage points away from Fortran in terms of performance. And this is several years ago. So today, it might even exceed Fortran. In fact, there has been cases where people had climate models written in Fortran. So some Professor Alan Edelman, one of the creators of Julia, he details in one of his talks some climate scientists that come to them with a climate model written in Fortran. And they have this idea that if they can just get 30% of the performance that they have with their Fortran code in Julia, they're on board. They're tired of writing in unproductive programming language like Fortran. They want something high productivity like Julia, and they're willing to pay something for it in terms of performance. It turns out when they converted their code, it actually ran 3 times faster. It didn't run slower. So that's a great testament, I think, to what's possible with Julia. Now, the other reasons that this is interesting is because the landscape of computing is changing fundamentally. We're not just running things on single-core microprocessors. In fact, we are increasingly utilizing heterogeneous computing. We're using graphical processing units. We have things like Google using tensor processing units. In short, we're using a lot more specialized hardware. And we have new techniques. Machine learning has been around for a long time, but is really hit it out the last decade or so, which is actually quite recent in terms of climate models and when they started getting developed. So to utilize all these different things and have a much more detailed climate model, Julia is very interesting. One of the reasons for that is that Julia is designed in such a way that it can very easily utilize all sorts of new hardware and run on different multiple computers. Now, I'd like to point out that Julia isn't only for scientific work. You can also find Julia or packages for all sorts of other things, like the Genie web framework, which is the Julia equivalent of something like Ruby on Rails or Flask or Django. So what exactly does Julia code look like? Well, here's an example. This is from the training course that I hold on Julia programming, where I go through an example of a rocket spacecraft and simulating a launch of this. So you don't need to understand what exactly this code does. It's not important for this talk, but I want to just highlight a few points about this code. So the first thing you'll notice is that this is not yet another curly braces programming language, right? By that I mean the ones where blocks are marked with curly braces, like Java, C, C++, C#, and so on. There's a huge number of these languages. Now, it might look like Julia has picked some kind of oddball syntax that nobody else uses, but this is actually a very similar syntax that you find in MATLAB, in Algol. You might see similar in Lua. So there's a number of scientifically oriented languages that use this kind of style. Ada, for instance, also uses this style. Pascal. So it's certainly part of another rich tradition. Not everything in computing is based on C. So a couple of things to notice here is we use keywords rather than symbols that mark the beginning and end of a scope. So we have while, end, if, end, and so on. Another thing you might notice, I highlighted that in blue, is that we often use type annotations in Julia. So we have some arguments here, spaceship, delta T, and max duration. And we're actually marking these off what type they are. The spaceship is a space vehicle. A second interesting thing to note is we're not writing that these are, say, int64 or float64 or something like that. No, we're saying they're a number. So Julia has something interesting with their numbers, They have abstract numbers. Numbers are actually part of a type hierarchy, which is a bit unusual in programming languages these days. And the third item, notice the delta T number. Yes, in Julia, there's a lot of usage of Greek letters or Unicode letters, and it tends to be actually pretty easy to use. Now, why is that? Well, because Julia is very popular in the sciences, where a lot of equations use a lot of these Greek letters. Okay, so let's have a little tour of the language. So these are the topics I'm going to cover. In the tour, we're going to look at sort of the basic things like functions, variables, loops, if statements, and arrays. What do they look like in Julia? Then I'm going to talk a bit about programming language trade-offs, such as why are dynamic languages slow? Some of the reasons has to do with what we call boxing and memory fragmentation. And what's the point of talking about these things? Well, the reason is that this helps us understand better what exactly the secret of the Julia programming language is. Why is it running so fast? To understand that, it helps to really understand what it is that makes dynamic languages in general slow. Then we're going to get a lot deeper into the technical details, talking about how Julia does its just-in-time compilation, code generation. So we're going to look at some examples here, what we call lowering of code, abstract syntax trees, and actually look at the LLVM bytecode. If you don't know LLVM, this is the low-level virtual machine. It's a kind of a compiler framework that's used a lot by Apple, for instance, for its C compiler, C++ compiler, Objective-C, Swift, and so on. And lots of other languages use it today, such as Rust, that comes to mind. And finally, I'm going to show you just a short list of basically Julia one-liners. I just want to show you that once I convinced you why this language pulls off being fast, I want to show you this is also an expressive language. It's a language that you can be very productive in addition to writing high-performance code. So the way I'm going to cover this language is by showing you examples from what we call the Julia REPL, or read, evaluate, print loop. So the way this works is you just type some expression, 2 plus 4, for instance, hit enter, and you get it evaluated and REPL. And Julia prints out the result, 6 in this case. Or the second example here, I do print hello and then hit enter, and then we get the out. So this is a very common way to work with Julia, to write things and get immediate response. You'll find this in a lot of other dynamic languages, but I think it works in particularly well in Julia. So let's do the simplest possible program you can do, hello world. So we do print line, and you can see it's Unicode enabled, so we can say that in Chinese as well. Now, I'm not going to be able to cover every possible little feature in Julia. This is not meant to be an extensive course on Julia programming, so I'm just going to pick some parts that I think is interesting. So the next thing I want to talk about is composite types. So I thought it's useful here to make some comparisons. So Python is a dynamic language just like Julia. C and C++, on the other hand, is a statically typed language. So in principle, an entirely different kind of programming language. Yet, as you will notice here, the C and C++ code looks more like the Julia code. Isn't that weird? It's a little bit different. You can see I highlighted in blue is the type information. So in Julia, we swap the type information. We put it at the end instead. Kind of a bit more like Haskell, for instance, or Pascal as well, Ada, and so on. So why are there these differences? Well, for Python, it's easy to point it out. it's a dynamically typed language, and the fields come into existence as you're running code. So the underscore init method here is what is code that is initialization code, I guess, run when you create a night object. And you do, say, self.name equals name. This is how these fields come into existence. In C and C++, of course, these fields have to be defined at compilation time. So when the program runs, we know that it has these fields. Julia is a little bit similar. You want to define what fields are here, but these fields or this type gets created at runtime. It doesn't create it at compilation time. Yet, you cannot change fields in Julia. So that's why there's a little bit similarity with C++. And you don't actually have to write the type information, but this is what's common in Julia. You write that, so in this case, that the knight has a name, which is type string. It has a health, and we're going to have that as an integer value, and the same with the armor. So let's look at how this works. Out of the box, Julia gives us a constructor, so we don't have to write that ourselves like in Python. And it also gives us a string representation. So you don't have to create a method that translates this data into a text string. We can access individual fields like the health. And to show you that this is not a statically typed language, but it's all very dynamic, let me give you an example here. We're going to create the Black Knight Ceremorian with health of 6 and armor of 2. You could access the name with .name, but when you're doing that, actually under the hood, what you do is call a function called getField. And the second argument is the field you want. And now this is what we call a symbol, but for those of you who are not familiar with symbols, they're very similar to text strings. You can think of this as a text string. So you're giving this function a text string on the field that you want, and then it returns it. And this is actually what happens when you do .name. In fact, you could even use an integer and then say, I want the third field, which is the armor one. So you could be getting the name of the field from the user at runtime or the network from a file or wherever, and call this. So this is all determined at runtime. It's not a statically typed thing. It's not a compilation time thing. Okay, let's look at some of the control structures like for loops. So it comes in different flavors or variations. We can loop over the elements here in purple, like an array. We can loop over a range from 3 to 5. And unlike in a lot of other languages, this colon is not some kind of special symbol that only works in the context of a for loop. No, the colon is actually an operator that constructs a range object. So you can actually store a range object in a variable, and then you can iterate over it. So in Julia, the for loop, what it really does is it iterates over objects that are iterable. And in fact, the for loop is not alone in doing that. All sorts of functions in Julia act that way. So the sum type, for instance, it adds up elements on objects which are iterable. So we could add up the elements of an array or the elements in a range. Doesn't matter. Now, if statements, not that exciting, but they're quite different in Julia from what you might be used to in other languages. For once here, I don't write return large or print large. I'm just putting a text string here. Why is that? Does that not look weird? Maybe this gives you an idea. This is the honorary operator, the question mark, and you might have seen that in Java, C#, C++, and so on. So this is used to return a value to S. And in fact, this is how Julia if statements work. So depending on what statement is true, so if X is larger than 1,000, then the large text string will be returned. That's going to be the value of the whole if statement, and it's going to be returned and stored in the s variable. Now, why is this? It's because in Julia, everything is pretty much an expression. Because Julia is it's a multi-paradigm language, I guess, but it's a very functionally oriented language. It's not a typical object-oriented language or imperative language. But let's look at functions. So as a kind of functional language, functions are naturally important. It's a big deal in Julia. You're building pretty much everything up using functions. And because this wants to be a kind of mathy or language, we want to make it easy to write those kind of functions. So you can see writing a one-line function in Julia is very easy. If you want multi-line functions, you need a function and an end keyword to mark the beginning and the end of multiple lines of code. And as you can see here in blue, I added some type annotations. You don't have to add them, but here I'm saying that the x and the y has to be some integer. This is a shorthand for a int64, a 64-bit integer. So here's an example of calling them. F of 3, it's going to give us 10, and add 3 and 4, well, it's just going to give us 7. Arrays is a big deal in Julia because it's important for scientific work. We tend to work a lot with tables of data. So you can think of this as a spreadsheet like Microsoft Excel or Pages, as I'm showing you here. This is working with data in multiple columns, and we tend to do element-wise operations. Like you take imagine this is kind of like a shopping list. We have a bunch of items, and then we have the price for each item, and then we want to multiply the number of items we're buying of each type with the cost of each item, and then we get a total cost, and then we can add all of that up. Now, how could you do something similar in Julia? So we would want a column array, or column vector as we would call it, for amount. This is how you would create it in Julia. This gives us a column vector. And so we do the next part, the unit costs. Pretty straightforward. And now, how do we get the total cost? Well, we could do the accounts, and then notice it says dot star. This is how you do an element-wise operations. If I only tried to do star, it would mean I was trying to multiply amounts with unit cost as if they were a single object. But with the dot star, I treat it as if there are multiple elements here involved. And we get this result. Now, what if I wanted to create this whole table directly? Well, you can do that in Julia with the syntax. And you will notice that in this case, I'm separating, or rather I'm not separating the numbers with a comma. Instead, they're just separated by space. And what this does is it creates row vectors. So a table is really made up of multiple row vectors stacked on top of each other. We separate each row vector with a semicolon. This is how we get this array. And it's worth talking about how do we actually access individual elements. So this should be pretty familiar with you from working with one-dimensional arrays in pretty much any popular programming language. And then there are some languages, not all, but Python, for instance, or Go, you can take slices. So you say, give me the second to the third element, so these elements. And then it's not always practical to be able to have to remember how many elements we have. Sometimes we just want to say, well, just give me all the elements. And sometimes we might not even want to specify in one. We just know we want all the elements. So we just put a colon. That's a shorthand. But we can step this up because in Julia, we have built-in matrix or matrices, and we can slice matrices as well. So let's do the very simple case first, just getting a single element. So this is how you read it. It says, get the second row, the third column, and then the intersection of these is the element that we want. We apply the same logic to multiple elements. So this says, give me the second row to the third row, and then give me the second column to the fourth column. And then we get these elements. Let's do that again. It says give me the second row, and then all of the columns and the intersection of these gives me the second row, the elements on the second row. And it works exactly the same for columns. How about dictionaries? So this example, we're going to create the dictionary you see over there. It has two keys. They're text strings 2 and 4, and then they map to some integer values that are the same, 2 and 4. We can write this in this way, and notice this rocket symbol or arrow. You might think that this is special syntax only applies when you're creating a dictionary, but you will be wrong. These are operators, just like kind of the colon. They are made, or they're used to create pairs. So I could create a list or an array or a vector of pairs, and then I can just provide that to dictionary. Have the same effect. I don't necessarily need to have pairs. I could use tuples. Now, tuples are a bit different from pairs in that you could have multiple elements in a tuple, but if you have a bunch of tuples with only 2 elements, well, they're essentially the same as a pair. So that's also a version. If you don't like that choice, well, you could always do the words and the numbers, or the keys and the values, into separate arrays, and then you zip them together to create an array of pairs. So let's create one of these dictionaries. You can see we get a nice printout of what's in the dictionary, and Julie just gives us this for free. Accessing elements, pretty much as you would expect. Assigning, as you would expect. And now you can see these extra elements added. Okay, let's do a little bit of functional programming, right? We're going to look at working with functions as first-class objects. So the first thing I want to talk about here is anonymous functions and closures. So why are anonymous functions handy? So consider this example. We want to map the square function onto the elements, the green elements here. So I want to apply square to 2, 3, and 4. So square is here a function that takes the argument and then squares it. So the effect of this is that we get map will apply this function to each element and then collect up a list of results and return those. So what you see there is an array or a vector of all the elements, input elements squared. Now we don't really in this case care that this function is called square. So we can just inline it, as you see in purple, with an arrow. So this is an anonymous function. It's just a function that takes an argument x and then squares it. So we don't really use a name here. We're just providing, what are the arguments. But what if we wanted multiple lines? What if this function is larger? Well, it's not very practical to write it this way. It turns out, though, that Julie has a very nice shortcut or syntactic sugar, which is the do end form. It works exactly the same. So these two cases are identical. So when you see there's a do form, you have to imagine that this is as if you took the function the do form creates and give it as the first argument to the function. So this is not particular to map. You could create your own function, and as long as your first argument is a function, you can use the do end form. Another cool thing is something called partial application. So this is a way that you can create new functions by only providing some function arguments. For those of you who have done some functional programming with, say, languages like Haskell, you would be familiar with this. The Julia solution here is not quite as fancy. It's not like this just sort of automatically works. You actually have to implement these solutions yourself, but I'm going to clarify that. So let's say we have an example. You have an array of elements, and you want to find the index for when an element has the value 6. So we can provide an anonymous function that takes a value and then compares that to 6. So you can see in this case, it will return 3 because the value 6 is the third element. Why not the second element? Well, because Julia has one base indexing. The first element is 1. But here's a nicer way of doing that. So you have the equals symbol, and you just give it one argument. You don't give it 2 arguments, just 1. And when you do that, instead of returning a true or a false, it returns a new function, and this function expects the first argument that you never gave. And so this is the function being applied to each element. So this allows us to do the same comparison. We can do this for a number of operators or functions. So in this case, asking is the elements larger or equal to 6. And then we get back that only the elements that are larger or equal. This is filter. So we get 6, 7, and 6. Now, the larger than and less than are already built in. When I first wrote these slides, it wasn't, but it's very easy to add yourself. So to add this, in Julia, we have this idea of functions and methods being separate. Methods in Julia is not the same thing as methods in an object-oriented language. There aren't any classes or inheritance as such in Julia. So instead, functions can have methods. And so what we're really doing here is we're importing the functions larger than and less than, and we're adding our own methods to them. So we're adding, or you can think about them as a flavor or a special variant of the function that we're adding. So we're adding a flavor where the larger than takes only one argument, the y, and then you can see instead of returning a Boolean value, we're actually returning a function, right? The arrow here tells you that this is an anonymous function that we're returning. So how does this work? Well, here how we would use it. Find first, well, find the index where the element is larger than 6 or less than, and so on. So let's do programming language trade-offs. What are the things that make dynamic languages slow? So the first big thing is boxing and cache. So there's an overhead here that applies to most dynamic language. But in fact, it doesn't only apply to dynamic languages. It tends to also apply to object-oriented languages. So that's a little hint to you on why Julia is not an object-oriented language. It's not a great thing for high performance. So in this case, if you compare it to Java, for instance, if point is not a sealed class, if it's not a final, you have the problem that there could be subclasses. So that means that there's some overhead in storing this point in memory. We have to store things like what type, like a tag that says what type is this, because you could have a variable of type point, but which actually points to an object which is a subclass of point. So that's why you need to actually store the type in. And then there's things for the garbage collector, such as mark, because in Java, everything is by reference. So you're kind of pointing to objects that might need to be garbage collected. And then there's things like alignment that you have to deal with. If you compare this to Julia, but that kind of also applies to languages like C and C++, you don't get this kind of overhead, or at least not most of the time. Instead, the values are unboxed. You just have the X and the Y that you're actually interested in. So how much does this actually matter? Well, actually, it starts getting a bigger and bigger problem as you create larger objects. So say that I create a rect class, a rectangle class, and I define that as the minimum and the max of the extent of the rectangle. Well, in a language like Python or Java and so on, you end up with this situation where the min and the max point to some point object. And you can imagine you can create this ever more complex. And in each case, you get this elaborate object graph. And in every case where you're using an object, you have all this overhead with the type tags and the mark for the garbage collector and so on. In a language like Julia, on the other hand, this all forms one compact, contiguous block of memory. So you avoid fragmentation of memory. And in fact, this only gets worse when you're working with arrays. So say that I'm creating an array of 3 points in Java. So Java cannot really know how much space each of the points take because there could be subclasses that have more member variables. So we need a point to some location in memory where the actual object lives. Again, you get memory fragmentation. And memory fragmentation is not good for cache behavior. It means you get more cache misses, which means lower performance. In Julia, on the other hand, there is no inheritance. So when you specify the vector and you say it's made out of points, Julia knows exactly how much space we need for each point. And it sets aside that amount of space for every point. So this is 3 points, and we set aside memory for that. That means you get everything in contiguous memory, and we don't get the memory fragmentation. The next problem is most languages have not been made for just-in-time compilation. In fact, most dynamic languages have not been made for this purpose at all. So Julia is a bit special. It was actually designed for just-in-time compilation. So why are dynamically typed languages generally so bad for just-in-time compilation? Well, that's what I'm going to show you here with an example. So we are going to have a Julia version. It's kind of going to be like a bit of like pseudocode. We have a simple case here. We have some 2D vector. If you don't know what vector is, it's kind of displacement in a coordinate system. So if you look at the orange dots here, these are points. And vectors are the arrows between the points. So we have the U here. It has the displacement along the x-axis of about 2.5, and then 1 in the y-axis, and so on. So I've added a very simple method here, or function, called multiply. It takes a vector and multiplies it with a coefficient. Not very complicated, right? This looks like a very simple, small calculation. So just to show you how this would work, here I create a vector v, and then I'm going to multiply it with 2, so we're going to get it twice as long, right? Hopefully no big surprises here. This is not supposed to be a complicated case. So what actually happens in the dynamic language? Well, this is a kind of a rewrite or like a pseudocode of what will be going on in a dynamic language, but I've actually used functions or that works or that exists in Julia. So it's a little bit like a pseudocode of how Julia would operate at a sort of conceptual basis, but it's not exactly what happens. So why is this slow? So the first thing is you got to look up every field, the X and the Y, right? The dictionary lookup. That's not fast to do something simple like that. Every time you got to do dictionary lookup. Next thing is we got to actually check whether each value actually is a float 64. That's we're assuming that it might not be that. Then we got to check the coefficient argument, right? That could be all sorts of types, and every type has to be handled in a particular way or a different way. The assembly code instructions for adding or multiplying an integer is different from doing it with a floating point value. So we need to do proper conversions before we can deal with them. So why is it that we need to look up fields? Well, the primary reason is that in a dynamic language, the type of a field could change. So we got to actually check that it's a floating point value, because suddenly it could be a text string. So if you compiled some code that assumed that they're all floating point value, that would be bad, because it could suddenly not be, and then your code would crash. So you have to do that check. The other thing is we have to actually look up the fields, because in a dynamic language like Python, JavaScript, etc., a field could suddenly disappear. It might not be there. So it would be very bad if we had code that just tried to access that field and it wasn't there. So this gives you a little bit of a hint of why Julia has added a couple of restrictions that don't normally exist with dynamic language. So one of those restrictions is that the types cannot change. You can't just change the type of a field. You cannot add or remove fields from a type. So, what's the secret then? I've given you a little bit of hint, but let's talk about what it's not, because people have so often misconceptions about Julia. And this matters, like these misconceptions, because I find that if I go over the things that make Julia run fast, people will still come and they'll ask, or they will get away with this, like, okay, so it's a just-in-time compiler. That's really what makes it. No, not really. And why does this matter? Well, it's because people very easily get into this idea that they don't need to learn Julia. They can just sit back and wait for the same just-in-time compiler to just be ported over to Python. So the idea is, hey, just tear off that just-in-time compiler from Julia and just stick it back in Python. And I don't have to waste my time learning this entirely new language. Well, I'm sorry, but it's not that easy. To give you a little hint, something like PyPy or Numba, these are existing just-in-time compiler solutions for Python. They existed much longer than Julia, and these are probably much larger, more sophisticated projects. The thing is, the Julia just-in-time compiler isn't a really fancy thing. It's a simple method compiler. That's not where the value is in Julia. A simple method compiler is not something that is all that much value to an existing language. So, obviously, Julia couldn't do its magic if it didn't have a just-in-time compiler, but it's not really the secret sauce. You can't just take that off and stick it to another language. Well, what about type annotations? This is a very common thing. It's like people look at some Julia code and they see, oh, I see an int there and a float and so on. They got type annotations, and these are the ways that you get things fast. And one thing that's bad about this is that people that are new to Julia, they start annotating a lot of their arguments, thinking this is going to boost their speed. It's going to get everything running much faster. No, in most cases, it's not going to make any difference at all. You're just going to make your code much less generic. Now, there's a good reason people think this, because this is how traditional dynamically typed languages gain performance, right? By annotating, you're telling it what the types are, so it doesn't have to do these checks like, is the type this or is it that? Julia doesn't need to do it that way anyway, so this is not the reason. So, at this point, you might wonder, well, what is the secret sauce then? Tell me. Well, the short answer is it's all about language design. It's not really about fancy compilers. So, what is this language design then? Well, for one, it's designed from the ground up to be used for LLVM. Right? In most other languages, just-in-time compilers came after the fact. The languages are already made. The other thing is programming style and idioms. So the standard library has actually been designed around this, knowing this is how it's going to be used, so that you start following a pattern in how you write your code so that it's high performance. And this is a key point to remember, because I see a lot of people, there's all these blogs and examples of people that take their Python code and just do a very straightforward translation to Julia, and then they come back and they complain that, oh, it didn't run any faster, or maybe it was even slower. And the reason for that is that they take style and idioms that make sense in Python, but don't make sense in Julia if you want to write high-performance code. And ironically, this is a little bit backwards, right? The way you write fast Julia code is often fairly straightforward, and it's a lot of the things, the sort of going through the hoops or the extra things that people do in other languages like Python and R and MATLAB and so on. To make those run fast, this is actually the downside in Julia a lot of the times. So that's important to know. If you're going to give Julia a try, at least familiarize yourself with the idioms and the style of Julia before passing judgment. And then finally, maybe the biggest one, or the most novel one, is what we call multiple dispatch. There is no mainstream language today that has multiple dispatch as a kind of core feature like Julia. So it's a feature that exists in other languages, but it's a kind of a bolt-on or a tack-on, and it's not central to the language. In Julia, multiple dispatch is everywhere. Everything is built around this. It's a very powerful feature, and unfortunately, even though it's maybe not so hard to explain it, it is hard to get across the full implications of this on a larger scale, because it's not just for performance that this has effect. It also affects software engineering, like how you construct code, how you combine libraries. There's a lot to this, and I can only cover parts of it. So let me motivate multiple dispatch with an example. So we have archers, pikemen, and knights. And this is kind of a rock, scissors, paper kind of example. So we have that the archer, it beats the pikeman. Why? Because, the pikeman doesn't move very fast, and the archer gets to fire his arrow in the pikeman before he gets to the target. The knight, on the other hand, beats the archer because he can just ride fast up before the archer gets to loosen very many arrows. And then finally, the pikeman beats the knights, right? This is a kind of known thing for anyone interested in kind of old military strategy. The pikemans could stop a cavalry charge. Notice that I made a little bit of modifications there. I highlighted mutable. And the reason for this is that in this example, we are going to be modifying the health value of these combatants. And in Julia, on default, the structs that you create are immutable. You can't change them. So mutable means that we allow to change them. So this is a little bit of the functional nature of Julia. So let me give you an example of kind of how we want this to work. So if we create a pikeman of health 5, and then an archer of health 4, and then we have, and then a knight, and then we have the archer attack the pikeman. So it deals some damage. It didn't kill him, so we deal some more damage, and at this point, the health has gone down to 0, and the archer kills the pikeman. Notice the exclamation mark is not syntactically significant, but it's a convention in Julia. Whenever you modify one of the input arguments, or in a more kind of fancy jargon, whenever you mutate one of the arguments, we want to write the function names as having an exclamation mark at the end. So this is just to help us as coders to kind of identify where in my code am I modifying something. That's kind of important for maintainability, readability, and so on. And then we have the archer attack the knight, and things don't go as well. The knight kills the archer. So how would we implement something like this? Because we want to have these, depending on the arguments, we're going to do different things. So here's an example. Highlighted here, archer and pikeman. So there's the A and the B arguments. They're different types. We have an archer and we have a pikeman. And in this case, so we have a function called attack, and it has one method that takes an archer and a pikeman. But this function has yet another method, but this method takes an archer and a knight, and you can see it deals with things a bit different. If the knight isn't killed, we're actually subtracting health from the archer, and then if it's below or equal 0, then we write out that the knight killed the archer. And we have more of these methods. So in this case, this is a method added to the attack function that deals with an archer versus another archer. You can just pause this if you want to look at the code more in detail. It should be pretty straightforward, I think. So what about the other cases? You have a pikeman versus an archer. Well, you can just treat that as the argument swapped. You can do a pikeman versus a pikeman. That's kind of like an archer versus an archer. But you want to write out some different text. You want to write pikemen killed each other. And then pikeman and knight. So these are some of the examples, and we would have to keep on going. Now, these kind of problems pop up in many circumstances. This is another case. If you're working with geometric figures, because I was used to be interested in game programming, this is something I hit upon on many occasions, is you have these different characters, and you're going to check if they're colliding with each other, and they might have different shapes to represent them. You know, maybe some are using a circle, maybe somebody's using a square. And the algorithm that you're going to use depends entirely on both arguments, right? It's not just one argument that decides this. That's the object-oriented thinking. That's what we call single dispatch. One argument, the first argument, the this or the self, decides what particular algorithm that we're going to call. But in this case, both matter. So this is an example, a kind of geometry example. I'm going to walk you through and how this would work in different types of programming languages that use different forms of dispatch. So dispatch is basically, how do I select a particular method or a particular implementation of code to run at runtime. So this is for a dynamic language, and languages that would do this is Python, Lua, Objective-C, and so on. And in these cases, we have intersect between a hexagon and some shape. And in an object-oriented language, the first argument has some significance. It's the this or the self. So we're going to write hexagon.intersect to indicate this special significance of the first argument. So what happens first is that we go on hexagon, and it has a pointer and is a pointer that points to the class that this object belongs to. It belongs to the hexagon class. And we're doing a lookup. We're doing a lookup of intersect. So basically, it's kind of like a text string or a symbol. And we do a hash table lookup. So we ask the hexagon class object, do you have an intersect method? Nope, I don't have that. Well, then we'll just go to super. We'll go your super class. And in Polygon, well, lo and behold, there is a intersect. And that will point to some implementation that it might be the code that was parsed and turned into an abstract syntax tree. And this would be the case in Ruby, for instance. Maybe not Ruby 3.0 that's currently released, but at least it used to be the case a function will be represented as an abstract syntax tree. So it's the parse code as it exists in memory, and then we evaluate that to create our results. If it was Python, there would be some bytecode there. What about static single dispatch? This is C#, Java, C, C++, and so on. In these languages, at least in C++, you typically, classes don't exist as objects at runtime. They're just gone. Instead, we've collapsed the whole class hierarchy into something we call a vtable or a virtual table, where we have a bunch of virtual functions or pointers to functions, function pointers. And so when we're calling intersects, what we do is we do an offset. So the compiler has actually turned the name intersect isn't there anymore. It's just an offset into a table, like an integer offset into a table, and we find a pointer to some machine code and we run that. So that's pretty fast. Now, multiple dispatch, that's an entirely different beast. There's no special first object here. All the objects matter. So that's why we write intersect hexagon, comma shape. So what happens in this case? Well, we begin at function, or there's a list, there's a kind of a global list or a list in your environment of all the functions, and we look up and we find the intersect function. And for every function, there is a list of methods. So how does this work? Well, Julia will ask every argument, what's your type? I'm a hexagon. Well, what's your type? Well, I'm a circle. And so this forms a tuple, like a collection of types. And then we use that to do a lookup in the methods table. And this is not a hash table lookup. It's not a dictionary lookup. It's, well, conceptually, there might be some hash table lookups, but and caching and so on. But conceptually, this is a linear search. You start with, is this tuple match circle circle? No, because the first one is a hexagon. Is it circle square? Nope. What about hexagon square? No, the last one is a circle. Okay, so we finally get to hexagon, circle, and we got a match. If we didn't get a match, we would just keep on going. And we would get a match for shape, the last entry here, because a hexagon, well, we have to assume that hexagon is a subtype of shape and a circle is a subtype. You would have to actually write that in your codes for this to work. But this actually shows that it's actually worse than a linear search. This gets to kind of like O square, like you have to check whether hexagon is actually a subtype of shape and so on. And then you have to check if circle is a subtype and so on. So this gets hairy. And that's the reason why you pretty much never see multiple dispatch anywhere. It's super slow. Or if you don't do it the right way. This is a slow way of looking up. Anyway, when you discover this, you find the abstract syntax tree. So as I said before, that's the method as it has been parsed. And the just-in-time compiler will then analyze this. And often you don't have any type information here, right? Maybe it's like some add function or calculate function and has some arguments x and a y, but it's not annotated with an integer or a float or anything like that. So what Julia is basically going to use that as a template, and it's going to check what was the type of hexagon and circle. Did it use integers for the points that make them up, or did it use floating points, whatever. And it's going to use that to generate machine code, and this machine code then gets cached. So it stores that in the case that hexagon and circle are floating point values, you should use this machine code. Next time it does a lookup and maybe works with integers, it's going to generate new machine code from the same template and store that under another entry. But still, so you can reuse the machine code. It doesn't go out of date because types can't change, remember. But you still have the slow lookup, or do you? Well, it turns out that you're going to do this compilation for the code that calls intersect as well. And the Julia just-in-time compiler there is able to analyze, right, when it's compiling. It figures out that based on what the inputs are, it's going to know whether there's a hexagon or a circle or whatever it is that's coming in as an argument. And that means if it knows already this, where it's going to go in the lookup table, it can just go there directly. So you just skip this whole step. And that's generally what happens over time as you're running a Julia program. The just-in-time compiler will just identify all these things and just skip all this, and everything just eventually just turns into mostly machine code without these slow lookups. So that's why if you're not doing just-in-time compilation, if you're not doing a proper analysis of your types during a sort of just-in-time compilation step, this would not work. That's why languages like Python, Ruby, etc. Will be very poor performance if they use this approach. You really need just-in-time compilation for this to work. So let's look a little bit at how just-in-time compilation code works. We're going to do that by kind of simulating a Julia JIT in Julia. To do that, I got to talk a little bit about how assembly code works. Normally, you just use the same plus symbol, whether you're adding two floating point numbers or integers. But at the microprocessor level, the CPU level, there is no plus operator. What you have is special assembly code instructions that are different for integers, for floating point values, and so on, even for different bit lengths. So a lot of what a compiler does is looking at type information So a lot of what a compiler does is looking at type information and picking the right assembly code to generate. So what we're going to do here is we're going to just fake assembly code instructions. So I'm creating an add, which represents integer adds, and then v-add s single precision double or something like that, v-add sd, to represent floating point addition. So they're kind of like, we're just pretending we are assembly code instructions. And then the last one, don't complain to me about how Intel names their assembly code instructions. So this VCVTSI2SD is for converting an integer to a floating point value. And you can kind of read this as vector convert signed integer to single precision double, something like that. So we already have an add symbol in Julia, so we're going to use this other add symbol, and we're going to register a whole bunch of methods. So we're going to have a method for when we got integers, when we got floating points, and when we have an int and a float, or a float and an int. And here you can see the cool thing, right? We are able to do what you typically want a compiler to do, which is pick the specific assembly code instruction that is applicable when you have, the given types of arguments. So let's use the REPL to show how this would work. So this is adding to this function has two numbers. Works fine. You can change it like this. Whenever you have a symbol as your function name, you can write it in infix form. So that's why a plus in Julia is really just a function. It's not. There's no special thing called operator. What you might think of as an operator is really just a function that is a single symbol, and because it's a single symbol, you can use it in infix form. Okay, so this kind of works as you would expect. Now we're going to use a macro called lowered, code lowered. And what that gives us is the first step of what the Julia just-in-time compiler would do, where it kind of turns more higher level Julia code into more low level Julia code, which is easier to compile. If you look at this, the kind of low level Julia code you get, if you look at the green here we see what it costs. So we use two integers, and in this case, it's picking the integer add. But if we do an integer and a floating point, then it picks both the conversion and the floating point add. So you can see that this is kind of doing as we would expect. To floating point values, it only calls our fake assembly code instruction for floating point adds. So that is our fake stuff. Well, yeah, let me just show you how you show so if you do methods, I get a list of all the methods for this function. So you can see all the different variations. Now, we're going to look at what the actual just-in-time compiler does in Julia. To be able to do that, it helps just put stuff you want to check inside another function. So we really want to just look at how add works. So we're putting that in another function called f. And in this case, we use a macro called code native. And what that does is it tells us what Julia will turn this expression into when it's compiling. And that just turns into a single instruction, load effective address. That sounds a little bit weird, but this is actually the equivalent of an add. Don't ask me why. This is just Intel assembly code. It's a bit weird. So it's dealing with these two registers called the RDI register and the RSI register, and then it's storing the result in the RAX register finally. This is also a little bit of a hint of why method JITs are simple, because and why they're very handy while you're developing, because compilation happens only at the level of each method. So that means that before I really run my full code, I can just introspect individual functions with particular arguments, and I get the method that's going to get called and what kind of code this would compile to. So it's very easy to kind of have a sense of, how well does the just-in-time compiler work. If you work with something like V8, the JavaScript compiler, this is a tracing compiler. And you have no idea what exactly it's going to do at runtime, because it's going to analyze whole traces of code, like a whole sequence of code being executed, and just how frequently is this being executed. And depending on that, it's going to choose whether it's going to do a just-in-time compilation or whether it's just going to keep on interpreting. With Julia, it's a lot simpler than that. Julia, every time you call a method, it's going to try to do a just-in-time compilation. So that's why we kind of like to say that, the Julia just-in-time compiler is not some kind of $100 billion type of compiler. It's relatively simple. So what if we do two floating point values? Then we're calling this vector add single precision double. So you'll notice that Julia does the right thing. It just produced a minimal amount of assembly code. You couldn't get it any smaller in C or C++ than this. And it does this without any type annotations. We could expand this operator. So here's an example of, I can add, it doesn't need to be just like low-level stuff, like just different number types. I could have a vector, for instance. So now I added a method that deals with vectors. So you can see that it picks out the right type and so on. I don't want to go too much through this. Point of this example really is to show that you can utilize this thing of how you can add methods just just to deal with kind of low-level things like, am I dealing with integers or floating point? But also for high-level stuff, like you can add more complex objects like vectors, maybe matrices, or pretty much anything. So if I do methods here, we have these vector versions added. So now we looked at a very simple example, but just how powerful, or really what can a just-in-time compiler accomplish? Well, that's what we're going to look at in this next section. I'll just call this just-in-time magic. So to illustrate this, I have this example of a function, a one-liner, that takes an argument, an x, and we haven't typed this. There's no type annotations. And we do multiply with 2, and then we add the same thing, multiply with 3. So how many assembly code instructions should this generate? Well, a kind of naive assumption here would, I guess, that there would be 2 multiplications, right? 2 times this x, and then we have some addition at the end. So about 3 assembly code instructions for this one. And then we have the foo. Now, this one we should expect to be quite complex. There is no type annotations here. It takes a variable number of arguments, and then it uses high-level stuff like a map, and it takes a function in here with the do-end form. So however the map is implemented, it's not going to know whatever it's going to come in, right? So very dynamic. And map is also implemented in kind of what I thought was the most convoluted way. So at a runtime, I'm asking what's the type of the x, and then I get a type object, t, and then I use that type object to convert the 2 and the 3 into whatever type x is. So if x was a floating point number, I turn the 2 integer into a floating point number. And then at the end here, we're doing these coefficients that we create, multiply them with the x, and returning that, and then the map will collect this, and then at the end, we're summing up all the values we collected in a dictionary. So the point here was, I thought, well, we're dealing with like stuff like type objects. That's kind of abstract stuff. So we should assume that this would generate whole reams of assembly code to deal with. Well, let's check that out. So we call bar w1 just to see, that it works as you would expect. With 2, well, that's basically 2 times 5 gives you 10. Foo is kind of made so that when you only give 1 argument, it's going to fundamentally do the same as bar, but in a very convoluted way. That's kind of the point. If you get multiple arguments, it's doing kind of the same as bar, but then we're adding up the results. So that should naturally give us 15. So let's look at bar with an argument 7. Do the code LVM thing again. Look at that. It's just one instruction, a multiply. And you can see there's a 5 there. So Julia figured out that 2x plus 3x is actually the same as 5x. So we can just simplify it to one instruction. But it doesn't stop there. If we do code native, so the code LVM gives us sort of a little bit higher level, slightly above assembly code. And this gives us the native Intel assembly code. So there's some further optimization here. And this is not even very easy to read, because aren't we supposed to do a multiplication here? And yet what you see here is just actually basically addition. Load effective address is an addition thing. So this needs a little bit further explanation. So what is going on here is that 2x plus 3x, it can be simplified. It could be simplified to 5x, but in this case, it's been simplified to 1x plus 4x. So the insight here is that things like 4x can be handled as shift operations. Anything that's a multiple of 2 can be handled as a shift operation. And it turns out that this load effective address it can not only add things, but it can also perform shifts. Shifts is very fast on a computer. You can do fast multiplication today, but in the past, something like multiplication was very slow. But here, there's no multiplication. We're just doing some shift operations and addition, and it's all done in one operation, so very fast. How about if we do it for foo, right? The convoluted way. And look at that. It just turned into one single instruction. So Julia just cut through all of this complicated crap, and if you ever feel like it, you could look up the implementation of map, and you can see that there's a lot of code involved there. In fact, just something like adding two numbers in Julia involves quite a lot of code. But it doesn't matter. The just-in-time compiler will turn it all into just one single machine code instruction. What about two arguments? Now that's going to mean we're mapping over several values, and then we're going to do a sum at the end. In principle, we should be seeing a lot more instructions here. But even this doesn't give us very much. There's not even a multiplication here. All we got is an add and the load effective address. And this is, we'll actually need a little bit further explanation to see what actually LLVM did here. So I hope that this will help. So if you think about what's going on, a map takes two arguments. Let's just call them Z and W. And the internal thing in a very convoluted way does essentially 2x plus 3x. So that means it does 2z plus 3z and 2w plus 2w. So that's where I'm showing in the left side here. And then this again is going to be the same thing, and then we're doing sum. That's the final thing. We could rearrange and simplify this a bit. And then we can do the kind of same rearrangement, right? We're getting a 1 and a 4 because these are nice from a kind of shifting point of view. And this can be further simplified so that we add up the z and the v to get an x, and then we do x plus 4x. And hey, we're back at that single instruction that we used in bar. So that's why this just ends up in this simple way. Okay, let me round off with some one-liners. So here's something I use when I edit code. I thought is useful to deal with converting snake case to camel case. So you can see here I split how are you, and I split on the underscore, and then I want to uppercase the first of each word. But we're dealing here with multiple values. Well, no problem. In Julia, if you want to apply something, if you remember from earlier, to every element, you can just add a dot. So even if uppercase first was actually made to work with individual elements, it can work with multiple elements by just adding a dot. This works for any function. You can do this with your own functions. The same with parse. So parse says it takes one argument, and then the first argument in it says what we want to parse to. We have some text string, and we want to parse it to an integer. By adding a dot, it means we can take a split is going to return 3 string values, and then we're going to apply parse with an integer to each of these, and then finally at the end we get an array, and then we do destructuring of this. So we're piecing apart this array and assigning each element in this array to individual variables x, y, and z. You can see that that's what we get here. So what about the factorial of 5? This is a built-in function. How do we implement this? We can just use reduce. So because multiplication is not like some special operator, it's just a function, and as a function we can pass it as an argument to reduce. The next thing in reduce is something that's iterable, so I can have a range object 1 to 5. So here I'm applying multiply to each element in this range object. Here I'm creating colon separated values. So we do string, and string would typically take one argument and turns that into string. But with the dots, we take multiple arguments and create multiple strings. And then we have these multiple strings. We give those as arguments to join, and then use colon to combine them. Now, if you remember from the example with the archers, because we don't have object-oriented programming or class-oriented programming in Julia, we cannot inherit. So we can't take, say, some soldier type, define health and damage, and then inherit. So we have to do basically what you see here. We we can have soldier as an abstract type, but it cannot include fields. So here we have health and damage, and we keep repeating this stuff. We don't want to repeat it, but Julia has a very powerful meta-programming facility. So what does meta mean, right? That's meta-programming is programming the programming, basically. So what we do here is we have a for loop, and we loop over some symbols. We store them successively in the T. And inside the for loop, we have this @eval. And what that does is it treats what you see in here as code that we're evaluating. So here is what we're actually creating a struct. And we're using the type, the name that we're using for this, as a variable. So the first time around, we're defining a mutable struct named archer. Second time around, one named pikeman, and so on. So you can do stuff like this to cut down on the boilerplate that you would get from maybe not supporting inheritance. Okay, I hope that this gave you an idea of what Julia is about, and you might want to explore it further. If you're interested, you could buy my book, Julia for Beginners. I'll have that in links. If you want to follow me at Twitter, you can see the handle there. Anyway, thanks. Let me know what you think.